Hello there, and welcome to the Sleep Science Top 1. Tonight, we are drifting back to the very beginning of all we know. Long before stars burned or galaxies spun, before time had a rhythm or space had a shape, the cosmos began its long and fascinating journey. The Great Expansion was never a moment. It was a movement trapped in the past. It is a narrative that is still being written in the deep structures of the universe, transported by ancient light and written over the night sky. This is not just an examination of our roots, but of our ties also. The atoms within you share a heritage with the earliest moments of the universe. The laws that shaped the first galaxies also shaped the universe around you in this very moment. As we explore this huge beginning, we will travel through mind-bending discoveries while uncovering secrets that are yet beyond the reach of science. If you love these pleasant trips, I ask you to like, subscribe, or share a thought below. It helps others find their way here too, one drowsy soul at a time. For now, there is nothing you need to do but relax. Allow your body to soften and your breathing to slow, and let the day melt away while we investigate the origins of the cosmos together. Let's begin. The Big Bang doesn't describe a bang at all. It depicts the expansion of our universe from a neist, the era of primordial ferocity. This concept is so potent because it is neither a myth nor a conjecture. It is a model that explains several very different clues with one coherent story. When we look outward, we find that distant galaxies tend to have light displaced toward longer wavelengths, and that shift grows with distance. An expanding universe is consistent with that trend. When we measure the cosmic microwave background of the sky, it matches what a formerly hotter cosmos should leave behind. When we count the lightest elements in ancient gas, the numbers match what a young, hot cosmos would have cooked. Put together, several lines of evidence turn a daring origin myth into something testable. The Big Bang is not merely a beginning. It is a framework that continually being verified against the sky. It was not an explosion in space. It was space itself spreading. Debris from a typical explosion shoots outward into an existing room. This beginning was stranger. The space itself expanded. This distinction contributes to the explanation of why there isn't a unique center to point to or an edge you may move in the direction of. Due to the stretching of the distance between them, every location perceives other far-off places moving away. This also explains why very remote galaxies can recede faster than the speed of light, without breaking relativity. Nothing is outrunning light through space. Rather, the distance between distant locations is shifting in size. This theory also impacts how we envision the early universe. It was not matter gushing from a single area. It was an everywhere that was once smaller, hotter, and denser, then expanded and cooled as a whole. The cosmos emerged as a pristine sea of fire before the first ripples of complexity began to stir. In those first whispers of existence, the cosmos was a sea of perfect stillness, with energy and particles scattered fairly uniformly. If it had kept completely smooth, nothing fascinating would ever have formed. Gravity waited for the slightest stutter in the symmetry to intensify. The unexpected twist is that the early universe did have minor differences, and we can still see their fingerprints. They were small, yet they were enough. Denser areas pulled in more material, tugged a little harder, and grew denser over a very long period of time. That runaway process developed structure from nearly nothing. The lumps turned into clouds of gas. The clouds formed the first stars. The stars gathered into galaxies. The galaxies coalesced into clusters. When you cast your gaze upward, you are looking at the universe's matured reflection of weak, early irregularities. Enlarged by gravity into a world full of shape, the oldest light we can see still fills all directions today. When the universe eventually cooled down enough for electrons to settle into atoms, this light started its journey. Prior to that point, the universe was like a luminous fog that was impossible to see through due to the constant scattering of light by unbound electrons. Once atoms formed, Light could travel large distances without being knocked around. Those old photons have been crossing space ever since, and they still arrive at Earth from every direction. Time has stretched their wavelengths, so what originated as hot, visible, or infrared light now reaches us largely as microwaves. Scientists were able to read a snapshot of the early universe by examining an all-sky light. This is not a portrait of celestial bodies, but a map of the void itself. It is an image from before they existed, and it allows us to test hypotheses about how the early cosmos acted. That afterglow is colder than deep space, yet it is everywhere. Today, that ancient background glow has cooled to only a few degrees above absolute zero. Empty space is typically portrayed as chilly, but this weak radiation sets a genuine temperature anomaly that permeates the universe. Although it doesn't appear brilliant to the human eye, sensitive sensors are able to measure it with remarkable accuracy. It also shows up in a surprise spot. A little part of the static you see on an untuned television has the same cosmic origin, coming after a journey that began long before the Earth formed. The afterglow is also remarkably uniform, which is a clue that the early cosmos was well mixed. At the same time, it contains microscopic variances that operate like a map of primordial conditions. In that sense, the coldness is not empty, it is information. For a short period, the cosmos was hotter than any star core. The hottest star cores reached tens of millions of degrees. In the early universe, temperatures were substantially higher. At those extremes, atoms cannot exist. Not even nuclei can endure. Matter becomes a seething soup of fundamental particles and radiation reacting continually. The very definitions of being were still in flux in the setting. Particle pairs are created from energy, and energy is created again from particle pairs. The cosmos is not a collection of objects. Physics itself is in a state of change. As growth continued, the temperature lowered, and the menu of potential particles altered with it. Certain species became uncommon, others stayed motionless. This is why early conditions matter so much. The particle physics of those moments help decide what materials the later cosmos will have available. When we build high-energy experiments on Earth, we are not just crushing particles. We are briefly recreating echoes of that primal heat. In the earliest minutes, the cosmos forged most of its helium. Stars are frequently linked to helium. However, a significant portion of it was created prior to the first star igniting. As the universe cooled from its first heat, protons and neutrons began to bond together. This was a narrow window. It was rapidly cooling, yet hot enough for nuclear reactions. Within minutes, most free neutrons were bound into helium nuclei because helium is very stable. That is why nearly a quarter of the normal matter mass in the universe is helium now, even in places with few generations of stars. Small amounts of deuterium and a trace of lithium were also produced by the same early mechanism. These abundances are not arbitrary. They depend on the density of ordinary stuff in the young cosmos. That is why measuring light elements in ancient gas can test the Big Bang narrative with astonishing accuracy. Every atom in your body traces back to early cosmic history. Some of your atoms have a lineage that starts in the earliest minutes, when hydrogen and helium became the universe's initial long-lived building blocks. Many others arrived later, built inside stars that lived, aged, and altered. Your biology is anchored by carbon that was created in star furnaces. When huge stars perished, the oxygen they produced was dispersed. Iron that delivers oxygen in your blood was formed in violent stellar ends. Even rarer materials, like gold and jewelry, are linked to exceptional processes when atomic nuclei are blown together under tremendous conditions. None of these stories replace the prior one. They layer on top of it. The early universe established the stage and supplied the basic simplicity. Later, cosmic generations added intricacy. It is accurate to say that you are composed of star material. Additionally, it is merely the middle chapters of a lengthier origin. Tiny early ripples developed into galaxies, clusters, and cosmic webs. Those early variations were not merely random bumps. They had trends that modern surveys can still discern. Ordinary matter alone would have struggled to cluster quickly enough because radiation pressure resisted collapse in the early age. An invisible component that interacts mostly through gravity offered more pull and helped structure grow earlier and faster. Massive filaments developed amid gigantic holes as matter poured into denser areas over time. Galaxies developed along these filaments, like beads on threads, and clusters coalesced where threads joined. This large-scale structure is one of the most stunning outcomes of simple gravity acting for a long period on little beginnings. It is also a big laboratory. Astronomers read these celestial fossils to gauge the universe grew and how much gravity influenced its evolution over cosmic time by charting the locations of galaxies and how their distribution varies with distance. Our existence hinges on a slight imbalance between matter and antimatter. In the heated early cosmos, energy made matter and antimatter in pairs, and those couples may annihilate back into light. Nearly everything would have cancelled out if the universe had produced precisely equal amounts, leaving only a thin layer of radiation. Instead, for reasons still being researched, there was a little excess of matter. After most annihilations finished, that minuscule residue produced the stuff for stars, planets, and people. This is one of the deepest outstanding topics in cosmology, since it ties the biggest scales to particle physics. The cosmos requires systems that handle matter and antimatter somewhat differently, as well as the appropriate circumstances for that distinction to be significant. Experiments explore small symmetry violations, while cosmologists hunt for signals in the sky. The existence of anything solid at all is proof that the early cosmos was somewhat biased. Timekeeping for the universe employs age calculated by cosmic expansion. Cosmologists read the cosmos like a clock embedded in space, rather than counting births. They measure how fast galaxies disperse at different distances, and how that pace has changed throughout time. Multiple records remain after expansion. It stretches light from distant galaxies, and it also sets the scale of patterns imprinted in the early cosmos that we can still measure today. When those separate observations match, they pin out a coherent timeline for cosmic history. In this way, even though no one was present to witness the universe's creation, we might conclude that it has any age at all. This method is also why discussions concerning the exact expansion rate matter so much. A minor alteration made today can transform the implied past and suggest that something significant is absent from our current understanding. The early universe was so thick that photons were trapped in a cosmic pinball machine. Try to envision navigating a storm of pure brilliance when every photon is quickly scattered. In the early ages, space was filled with charged particles, flying fast, and photons constantly hitting with them. Light exists, but it could not carry an image across any meaningful distance. The whole cosmos acted like an luminous veil that held the universe's secrets hostage. This detail is the keystone of our story, because it indicates that there is a natural visible limit to our cosmic story. We cannot see earlier than the point when conditions changed and light eventually started flowing in long, straight lines. Before that, the cosmos wasn't a void of shadow, but a prison of blinding radiance, too hot and too crowded for transparency. That early opacity also shaped what could form. With radiation intimately tied to matter, pressure fought gravity, and growth was forced to wait for the cosmos to cool and thin. When atoms originally formed, the universe suddenly became translucent. The universe once underwent a character shift that was akin to a curtain lifting. As temperatures lowered, electrons could finally stay bonded to nuclei instead of being driven away by intense collisions. Once most matter became neutral, photons stopped bouncing repeatedly and began to stream through space. That transition released the earliest light we can perceive. It also set the universe on a new route, since neutral gas acts differently from an ionized plasma. Gravity had a better chance of drawing stuff into denser areas. Pressure decreased, and cooling became more efficient. This is one of those instances where a shift in tiny activity rewrote the fate of everything on the greatest proportions. The early universe can be studied like a fossil because of this as well. We are still able to precisely map the vast amount of information left by a single transition. Hydrogen developed first, then helium, then a whisper of lithium. That tiny chemical beginning point fashioned the universe's personality for a long period. With nearly no heavier elements accessible, early gas could not cool easily. And cooling matters because it helps clouds collapse to produce stars. Since there are few methods for hydrogen and helium to release energy, the first star-forming regions had to be enormous, patient, and harsh. Although lithium was present in very small quantities, it was too uncommon to significantly alter the chemistry. Because of this, the earliest generations of cosmic objects were most likely considerably different from modern stars. Later on, once stellar activities began enriching space with heavier materials, cooling became more efficient and smaller stars could emerge. In a way, the early cosmos began with a very limited toolbox, and the complexity we see now was gained slowly via cosmic time and countless cycles of birth and death. Before stars ever existed, the first atomic nuclei were created. It is strange to realize that nuclear physics happened on a universe-wide scale before the first pinprick of starlight. In those earliest minutes, the entire cosmos was hot enough for nuclear reactions, and it was also growing rapidly enough to shut them down. That combination is important. Stars can remain fusing for millions or billions of years because gravity retains their cores hot and dense. The nascent universe had no such constraint. As it grew and passed the requirements for fusion, it cooled. Thus, the first nuclei were produced in a brief, worldwide nuclear assembly explosion, after which the chance was lost. This early chapter determined the basic composition of the cosmos, and it established the raw material from which later stars would build everything else. It is an origin narrative written in physics rather than flames. Neutrinos filled the universe long before the first atoms existed. Neutrinos are genuine particles, and they interact so weakly that they can travel through a planet with nary a whisper of contact. In the early universe, they were formed in tremendous numbers, and then they slipped away from the rest of matter when the cosmos was still extremely young. It would be a relic much older than the earliest known light if a background sea of these ancient neutrinos still permeates space today. Capturing these ghostly echoes remains one of science's greatest pursuits, because neutrinos rarely interact with anything. Still, their presence matters. They affect how swiftly the cosmos expanded in its initial moments, and they leave modest fingerprints on the growth of structure over time. In a way, the universe has been populated with unseen passengers since the beginning, carrying information from ages we cannot observe with light. Most matter today is not atoms. It is invisible dark matter. The calculations do not match what we can see when astronomers weigh galaxies based on the speed at which their stars orbit. Something invisible adds more gravity. The similar enigma emerges in galaxy clusters. If apparent substance is not enough to hold the system together, it also appears when mass bends light from background galaxies, which enables scientists map gravity directly without relying on starlight at all. Again and again, the maps reveal more mass than the atoms can produce. Dark matter is the moniker we give to the missing gravitational ingredient. It doesn't appear to glow or absorb light in the typical manner. However, it has a huge impact on the cosmos. The possibility that dark matter is a novel type of particle and that its discovery would extend physics beyond the well-known catalogue is one of the most intriguing possibilities in contemporary science. Dark matter molded the first structures by dragging gas into wells. Long before there were brilliant galaxies, dark matter began to assemble into clumps under gravity. Those clusters formed a structure that conventional gas could fall into. Gas alone would have had a tougher time settling early on because radiation pressure pushed back. Dark matter did not feel that pressure, so it could start creating structure earlier. Over time, Gas accumulated inside these invisible halos, cooled where it could, and eventually sparked the first stars. The brilliant regions we observe today are like lanterns hanging inside far larger black structures. And the first galaxies were born inside gravitational wells that already existed. Computer simulations depict this process in stunning detail. They create a cosmic web from tiny beginnings, and they produce filamentary networks that look substantially like what surveys of genuine galaxies reveal. It is a potent illustration of how visible architecture may be influenced by the invisible. Dark energy causes cosmic expansion speed up, not slow down. For a long time, many people expected gravity would gradually halt the expansion, like a ball hurled upward. Then, observations of distant exploding stars suggested the opposite. The expansion has been speeding for the last several billion years. Dark energy is the moniker given to whatever is driving that acceleration. It might be a constant energy of space itself, or it might be something that evolves throughout time. Either way, it impacts the universe's long-term future. Even in theory, far-off galaxies will disappear behind a cosmic horizon and become unreachable if acceleration persists. That does not mean the universe ends. It implies that as time passes, the visible universe gets smaller from our point of view. Because the most straightforward explanation involves vacuum energy, which is connected to quantum concepts that are still being worked out into a comprehensive theory. This discovery also establishes a connection between the very vast and the very small theory. Galaxies are speeding apart because space between them continues stretching. Expansion shows up as a link between distance and speed, and it makes the cosmos feel alive with motion, even when galaxies are not shooting rockets. As the scale of the universe rises, light moving across space gets stretched too, and its color moves toward the red. That is why redshift is such a fundamental tool in cosmology. It is more than just an indication that things are far off. Additionally, it indicates that during the light's journey, the universe underwent a transformation. Yet this stretching has limits in ordinary life. Because gravity and other forces hold bonded structures together, neither your body nor your solar system expands. In the vast voids between galaxy clusters, where nothing is strong enough to stop the expanding of distance, expansion is most noticeable. The night sky can be reframed by thinking this way. It is not a fixed dome of lights. It is a record of changing geometry. We perceive faraway galaxies as they were, not as they are today. When a telescope captures the light of a faraway galaxy, it is catching a message that has been traveling for a very long time. This indicates that the picture is historical rather than current. Some of the dim smudges in deep space images are galaxies from an era when the cosmos was still young, when stars were growing swiftly and structures were rougher and more chaotic. This is why astronomy is so distinct from most sciences. The universe offers you its past because you can't bring a galaxy inside a lab. It also indicates that the sky has layers, much like a timeline. Galaxies that are closest to us display older chapters, while those that are farthest away display earlier ones. With modern tools, we are stretching that time window farther back, and each step exposes how today's familiar cosmos learned to appear like home. The observable cosmos has a horizon because light has finite time. There is a boundary to what we can witness, and it exists for a simple reason. The universe has a finite age, therefore light has had only a finite time to reach us. Beyond a certain distance, even if something is out there, its light has not arrived yet. This generates a natural cosmic horizon. It is neither an edge of the entire cosmos nor a wall in space. It is an edge of information for us. Since expansion influences how far light can travel while space itself is expanding, the size of that observable region relies on how expansion developed over time. For this reason, cosmology seems like a rigidly regulated detective job. The universe gives us a sphere of evidence, and inside that sphere, we must rebuild the story using light, gravity, and the smallest patterns that persisted from prior eras. Some locations will never be seen, because expansion outruns their light. There are places where signals will never reach us, no matter how long we wait. This is not because they are concealed beneath dust or prevented by something in the way. It is because space might expand in such a way that the distance between us and those locations rises too swiftly for their light to make progress toward us. There may be an event horizon in a universe with accelerated expansion that differs from the boundary determined by the age of the cosmos. It distinguishes what can ever influence us from what cannot. That concept is exciting and scary at the same time. It implies that there might be enormous domains in the universe that are permanently cut off from our observations in the future. It also means the cosmos has an element of built-in mystery. There are certain chapters, however, they cannot be included in our proof. They stay beyond grasp, not by technology, but by geometry. Instead of acting like a gas, the early cosmos functioned like a plasma. A gas is formed of neutral atoms that generally disregard distant electric forces. The early universe was different. It was so hot that electrons were not attached to nuclei. Therefore, matter was formed of charged particles traveling in a dazzling sea of radiation. That condition is called a plasma, and it has a personality of its own. Waves can pass through it. Electric and magnetic forces are important, and light cannot pass through cleanly because it constantly scatters off free electrons. You have witnessed a little sample of a plasma in action if you have ever seen the glow of a neon sign. On the size of everything, the early cosmos was similar to that. The reason this resonates through the ages is the plasma stage creates the basic conditions for later structure. It influenced how pressure pushed back against gravity, how energy flowed, and how the universe cooled into the calmer atomic period that followed. The first sound waves in plasma left patterns in galaxies. In the nascent cosmos, pressure and gravity conducted a spectacular tug-of-war. Gravity tried to pull matter into denser locations, while radiation pressure pushed outward and resisted collapse. That push and pull sent waves through the heated plasma, and they acted like sound does in air, only the medium was a flaming mixture of particles and light. These waves flowed outward from early dense regions, and they brought stuff with them as they went. Then the universe cooled sufficiently for light to disconnect from matter, and the waves effectively froze in place. Radiation no longer propelled them, yet the pattern they had etched onto matter persisted. Much later, when galaxies formed, they inherited that ancient impression. So when astronomers chart where galaxies like to be, they are not merely viewing the work of gravity over billions of years. A faint echo of pressure waves from a time before stars existed is also visible to them. Those fossil sound waves are called baryon acoustic oscillations. The word sounds complex, yet the idea is refreshingly concrete. Those early pressure waves involved ordinary stuff, which scientists referred to as baryonic matter. The distribution of matter was left with a desired separation scale by the waves. Much later, that scale shows up as a modest tendency for galaxies to be discovered a particular distance apart, more often than random chance would predict. This small preference can be detected by surveys measuring millions of galaxy positions, making them an effective instrument. It acts like a standard ruler put in the early universe. When we witness that ruler at different distances, we are also observing it at different times in cosmic history. Scientists deduced how the universe expanded throughout time as a result. It is astonishing that a pressure wave in a primordial plasma can become a measuring stick for the geometry of space billions of years later. Cosmic background spots disclose temperature differences of just micro amounts. The old sky glow is incredibly uniform. However, it is not totally smooth. Satellites map the entire sky and discover little areas that are warmer and colder. The variations are so slight that they are measured in millionths of a degree, but they carry great meaning. They indicate that the early universe had tiny fluctuations in density and velocity, which later influenced what could grow. A multitude of information about the contents of the universe is also encoded in these spots. Their sizes and contrast depend on how much ordinary matter there was, how much invisible matter influenced gravity, and how radiation interacted with everything at the time. It is like reading a barcode inscribed onto the universe while it was still young. The pattern is modest, but it is consistent and measurable. Scientists are able to extract a detailed picture of the early conditions of the universe from that faint modeling. Those little distinctions generated the seeds of all later structure. A tiny advantage, given enough time, can become a kingdom. Slightly denser areas had slightly stronger gravity in the early universe. That extra pull helped them gather more matter, which made them denser still, which increased their pull again. This feedback transformed tiny fluctuations into massive structures over a very long period of time. The process did not happen smoothly everywhere. Some regions became the crowded neighborhoods of the cosmos, and others emptied into enormous voids. Gas eventually formed stars and galaxies inside larger gravitational environments as it fell inward, heated, and cooled. This is why the cosmos looks textured rather than uniform. It also explains why structure is such a sensitive test of cosmology. If you change the early seeds, you change the later landscape. Modern simulations begin with tiny fluctuations and let gravity do the rest. When the results resemble real galaxy maps, it feels like watching the universe assemble itself again. The afterglow of the universe has an almost perfect black body spectrum. The cosmic afterglow matches an ideal thermal curve with remarkable accuracy when spread out into its colors. Something that has been in almost perfect thermal balance, such as a hot object glowing smoothly instead of producing sharp lines, produces a black body spectrum. Because matter and radiation were closely combined and continuously interacting, that is precisely what the early universe should have produced. The stunning part is how clean the result is. Real systems often show distortions, impurities, or extra features. The cosmic background spectrum is almost immaculate. Instruments designed to measure it treated the sky like a laboratory source, and the match to a thermal curve became one of the most persuasive pieces of evidence for a hot, dense, early phase. It is as if the universe kept a receipt from its earliest era, and that receipt still checks out when we test it today. That spectrum is one of the strongest clues for a hot beginning. A thermal spectrum of that quality is hard to fake. Many alternative origin ideas might produce radiation, but producing a sky-filling glow with the right shape, the right smoothness, and the right temperature today is a tall order. The hot beginning picture predicted that such a relic should exist, and it predicted the form it should take once expansion stretched it into longer wavelengths. When measurements confirmed both the existence and the shape, it tied the model to a specific, testable outcome. It is also a clue that reaches deeper than a single observation. The same early conditions that create a thermal background also create the environment needed for the first light element nuclei to form, and they set the stage for later structure to grow. So the spectrum does not stand alone. It fits into a wider story where multiple independent clues converge on the same conclusion. That convergence is what turns an idea into a compelling cosmic narrative. In the early universe, protons and electrons could not stay together. Heat was not just warmth back then. It was a never-ending assault of vibrant light. Any time an electron tried to settle near a proton, a high-energy photon would strike and knock it free again. Electric forces were important everywhere, and the universe acted like a restless ocean of charged particles. This kept matter and light tightly linked, like dancers who could not let go. It also meant that atoms, chemistry, and the stable structures we take for granted did not exist in the universe. Everything was quick, reactive, and unfiltered. As expansion continued, the temperature dropped, and the relentless breakups began to fail. That shift opened the door to a new era, where neutral atoms could finally exist, and light could start traveling longer distances. It is amazing that the possibility of calm, stable matter depended on the universe cooling just enough. Recombination is when the great settling, where the restless dance of particles found its rhythm. This moment was less like a single spark and more like a grand settling of the cosmos. As the universe cooled, collisions became gentler, and electrons could finally remain bound to nuclei for long stretches of time. A significant shift in behavior was the outcome. The early universe's fog started to disappear because neutral atoms scatter light less violently than free electrons. Matter also began to act more like a gas than a plasma, and that changed how it could clump and cool. You can think of it as the universe switching from a loud, crowded room to a quieter space where signals could travel. The light released around this transition became the oldest light we can observe today. It is not a message written in words. It is a record written in temperature patterns and polarization, and it tells us what conditions were like when the universe first became transparent. Before stars, the universe entered a long cosmic dark age. After the first neutral atoms formed and the oldest visible light was released, the universe did not immediately blaze with stars. Instead, it entered an era with no new starlight at all. Space was filled with hydrogen and helium gas, and gravity was slowly gathering it into denser regions. But nothing had ignited yet. It was dark in the everyday sense, even though the universe still held a faint background glow that kept cooling as space expanded. This long pause matters because it was a time of preparation. Density peaks were growing, invisible scaffolds were deepening, and the first star-forming clouds were slowly taking shape. The Dark Age is hard to observe directly, which makes it one of the most tempting frontiers in astronomy. When we learn to detect signals from this era, we will be listening to the universe before its first lights turned on. The first stars ended the Dark Age by flooding space with ultraviolet light. The first stars were not just new objects in space. They were cosmic switch flippers. When they ignited, their intense ultraviolet light began to change the surrounding universe. That radiation could strip electrons from hydrogen atoms, turning neutral gas back into an ionized state in a process that spread outward over time. This transformation is called reionization, and it reshaped what the universe looked like and how it behaved. These early stars also began creating heavier elements inside their cores, then scattering some of that material when they died. In that sense, they were both lighthouses and chemical pioneers. Their light carved bubbles through the surrounding gas, and those bubbles grew and overlapped until much of the universe was affected. It is hard to overstate how dramatic this is. For a long time, the cosmos waited in darkness, and then the first stars began rewriting the transparency and chemistry of space itself. Early stars likely formed from nearly pure hydrogen and helium. Without heavier elements, early star formation was a different kind of challenge. Metals, in the astronomy sense, help gas cool by letting it radiate energy away. With almost none available, primordial gas had fewer ways to shed heat, so it tended to resist breaking into small pieces. That suggests the first stars may have been unusually massive compared with many stars today. Massive stars live fast and die young, and their endings can be violent enough to shape their surroundings. They also change the universe's chemistry by forging new elements, which later generations of stars could inherit. So the first stars may have been brief, brilliant bridges between a simple universe and a complex one. Even though we have not seen a true first-generation star directly, astronomers search for their signatures in extremely metal-poor stars that still exist today. Those survivors can act like living fossils, preserving clues about the era when starlight first began. The first galaxies were small, then merged into larger systems. Galaxies did not begin as majestic spirals and giant ellipses. They started as smaller gatherings of gas, stars, and dark matter that formed in the early cosmic web. Gravity then did what gravity does best. It pulled these early systems together. Mergers were common, and they were creative in a rough way. Collisions could trigger bursts of star formation, stir gas into new shapes, and feed growing central black holes. Over time, repeated merging built larger, more structured galaxies. This is one reason deep images of the early universe often show irregular, clumpy shapes. They are snapshots from a restless era, when the ingredients of galaxies were still assembling. Our own Milky Way carries the evidence of this history in its halo of stars and streams. Some of those stars likely came from smaller galaxies that were pulled in and absorbed. A galaxy can be a family tree written in starlight. Large-scale structure resembles a web because gravity amplifies small differences. On the biggest scales, the universe looks like a network. There are filaments where galaxies crowd together, nodes where clusters gather, and enormous voids where almost nothing lives. This web is not designed, it is grown. It begins with tiny irregularities. Then gravity magnifies them over billions of years. Where matter is slightly denser, it attracts more. Where matter is slightly thinner, it gets left behind. Over time, this creates long tendrils and vast empty regions that can span hundreds of millions of light years. What is especially fascinating is that this structure can be simulated. Start with a simple early seed pattern, add known physics, and let time and gravity run. The result is a universe that looks uncannily like the one we map with telescopes. When you look at a galaxy survey, you are not just seeing objects scattered randomly. You are seeing a fossilized flow of matter shaped by gravity across deep time. Most of the universe is empty, yet its emptiness carries energy. It sounds like a contradiction. Empty space feels like nothing. Yet the universe's expansion seems to be influenced by something that behaves like energy tied to space itself. This idea shows up when we compare how the expansion rate changed over time, and it leads to a startling conclusion. The cosmos is not only expanding, the expansion is accelerating. The simplest way to describe this is with a constant energy density of empty space, often linked to the cosmological constant. If that description is correct, then adding more space adds more of this energy, not less. That makes the future feel strange. As the universe grows, the emptiness becomes an active player in its evolution. This is one of the deepest puzzles in modern physics, because quantum theories predict vacuum energy in a way that is difficult to reconcile with what the universe appears to do. In a sense, nothingness is not nothing. It has weight in the story of the cosmos. The early universe expanded so fast that it smoothed itself out. One of the most puzzling features of the cosmos is how uniform it is on the largest scales. Regions of the sky that are very far apart have nearly the same temperature, even though there was not enough time for light to travel between them in the standard early picture. This is the kind of mystery that forces new ideas. A proposed solution is that the universe went through a brief period of extremely rapid expansion very early on. During that phase, a tiny patch could have been in contact and well mixed, then stretched to enormous size. It is like taking a small, smooth section of fabric and pulling it so wide that it becomes the background of everything you can see. This kind of expansion would also help explain why the geometry of space appears so close to flat. The remarkable part is that a short, early episode could set conditions we still measure today, long after the event itself ended. Inflation explains why distant regions share nearly the same temperature. If the universe inflated from a small, connected region, then parts of the sky that look unrelated today could have once been neighbors. That would allow them to come into thermal balance before inflation stretched them apart. After inflation, the universe continued expanding more slowly, and the ancient afterglow was released later, carrying a record of that early uniformity. This explanation is compelling because it turns a mystery into a consequence of a specific early process. It also makes predictions. Inflation should not erase all variation. It should leave tiny fluctuations with a particular statistical pattern, which later become the seeds of structure. So this idea is not only about smoothness, it is also about the texture that remains. When cosmologists compare those predictions with the detailed maps of the cosmic background, they are not just asking whether inflation sounds nice. They are asking whether the universe behaves like it truly had that early growth spurt. In that sense, inflation is a story about cause and evidence, stitched together across unimaginable time. inflation also predicts a pattern of primordial waves in space-time. If inflation happened, it should have shaken the universe in a very particular way. The stretching would not only smooth space, it would also generate gravitational waves, which are ripples in space-time itself. These would be different from the waves made by black holes colliding today. They would be ancient, spread across the whole cosmos, and born from the earliest expansion. Their strength would tell us about the energy scale of inflation, which is a clue to physics far beyond any machine we can build. Think of it like hearing the faint vibration of the universe's first great growth spurt. If we could measure that pattern cleanly, it would turn inflation from a clever explanation into a directly tested event. It would also connect the largest thing we know, the universe, to the smallest rules of quantum fields. Scientists hunt those waves through polarization in the cosmic afterglow. The cosmic background light is not a mere glow. It also has a subtle orientation, like light filtered through sunglasses. That orientation is called polarization, and it carries a record of what happened when the light last scattered. Gravitational waves from the early universe should leave a special curling pattern in that polarization, a swirl that is hard for other effects to mimic. The challenge is that the signal is faint and the sky is messy. Dust in our own galaxy can produce polarized light too, and it can masquerade as the very thing we seek. So this hunt demands patience, multiple telescopes, and careful cross-checks across different frequencies. It is a beautiful example of scientific humility. The prize is enormous, but the standards are severe. If the signal is real, it would be a direct whisper from the universe's earliest instance, carried to us in the orientation of ancient light. The Big Bang model is tested by many measurements, not one. What makes this story so persuasive is its teamwork. A single clue can mislead, but a web of clues that agree is harder to dismiss. Expansion shows up in the redshifts of galaxies. Light element abundances match what a hot early phase should produce. The cosmic background carries the thermal signature of an early, dense environment. Large-scale structure shows how tiny early variations grew over time. Each line of evidence has its own instruments, its own sources of error, and its own methods of analysis. Yet they converge on a consistent picture, and that consistency is the real triumph. It is also why cosmology keeps evolving. When one measurement disagrees with another, it is not an inconvenience, it is an opportunity. Tension may indicate new physics that is just beyond the scope of our current model, or it may indicate a systematic error that is hidden. Hubble's discovery showed galaxies beyond the Milky Way were real. For a long time, people argued about what spiral nebulae were. Some thought they were small clouds inside our own galaxy. Then Edwin Hubble measured a special kind of variable star in one of these nebulae and used it to estimate distance. The result was staggering. The object was far beyond the Milky Way, which meant it was a separate galaxy. The universe grew from a single island of stars to a sea of islands in a single step. That shift changed everything about the question of origins. The universe has a rich past that needs to be explained if there are innumerable galaxies. It also reframed our place in the cosmos. We were not near the center of a single system. Among many galaxies, we were in one. That realization set the stage for interpreting redshifts as evidence of an expanding universe, which later became a pillar of modern cosmology. Expansion was first interpreted as galaxies receding from each other. The most straightforward image that emerged when astronomers discovered that many galaxies had redshifted light was motion. Redshift was similar to the Doppler effect, a siren that changes pitch as it goes by. If light is stretched, the source might be moving away. That interpretation made the universe feel dynamic and surprising because it suggested that space is not static, it is changing. Over time, the deeper explanation became clearer. The redshift is not only about galaxies moving through space, it is also about space stretching while the light travels. Nevertheless, The historical significance of the recession image lay in its ability to persuade people that the universe had a timeline. If distances are increasing, then in the past they were smaller. That simple reversal points toward a hotter, denser beginning. It is a powerful example of how a straightforward observation can pull an entire worldview into motion and then force it to grow more subtle as understanding deepens. Georges Lemaitre proposed an expanding universe before it was popular. Lemaitre was both a scientist and a priest, and he approached the cosmos with a rare blend of imagination and mathematical discipline. Working from Einstein's equations, he argued that the universe could be expanding, and he connected that idea to observations of galaxy redshifts. He even suggested that the universe might have begun from an extremely compact state, a seed that later expanded. Many people at the time, including Einstein at times, favored a static universe. Lemaitre's work shows how scientific progress can require not only data, but also the courage to take equations seriously when they point somewhere strange. His legacy also serves as a reminder that people, whether early or late, skeptical or convinced, are the ones who construct cosmology. Ideas need both boldness and evidence. Lemaitre provided the boldness, and later observations helped provide the evidence that made expansion difficult to ignore. The phrase Big Bang began as a mocking nickname. The name has stuck in part because of its dramatic sound. It was coined during a period when cosmologists were arguing about how the universe began, and not everyone liked the idea of a hot origin. The phrase was meant to sound a bit silly, as if the whole concept were too explosive to be serious. However, language has a gravity of its own. The argument that gave rise to a memorable label may not last as long. Over time, the name became a convenient handle for a complex model, even though it can mislead people into imagining a bomb going off in empty space. That is the irony. A mocking nickname became a household term, and it helped the public remember an idea that is subtle and mathematical. It also shows how scientific stories spread. Words influence how ideas spread throughout culture, but data may resolve disputes. Sometimes, a phrase can carry an entire concept into the public imagination, even if the phrase is not perfectly accurate. Penzias and Wilson stumbled onto the cosmic afterglow by accident. They were not trying to confirm a theory of cosmic origins. They were trying to solve a problem in their radio antenna. They were unable to get rid of a persistent hiss. They checked equipment. They thought about interference. They even had to deal with the equipment's actual mess. Yet the noise remained steady and coming from every direction. That is the key detail. A local source would vary with pointing direction or time, but this signal seemed universal. At the same time, other scientists had predicted that a hot, early universe should leave behind a faint background of radiation. Prediction and accident were strikingly similar. It is one of science's most charming moments. An engineer's nuisance became a cosmologist's treasure. It also shows how discoveries can arrive sideways. The universe can occasionally be discovered while attempting to repair a machine that won't stop listening to the sky. A faint hiss in radio antennas helped confirm a hot early universe. The discovery of that all-sky radio noise did more than add one more fact. The entire model's status was altered. Without a relic background, a hot early phase could be dismissed as speculation. With it, the universe carried a direct thermal fingerprint of its use. That hiss was not a signal from a star, or a galaxy, or even a cluster. The glow was a diffuse remnant of a period when the source was the universe itself. It also helped settle a major debate between different cosmological pictures, because the steady-state idea had no natural reason to produce a sky-filling thermal background with the observed properties. The hiss provided a tangible anchor for the narrative, but it did not tell the entire story on its own. It is remarkable that something so cosmic could first appear as an irritation in a receiver, like the universe insisting on being heard. CoB measured the afterglow spectrum with stunning precision. Although the cosmic background had been identified by the late 20th century, its precise form was still important. A hot early universe predicts a very specific thermal spectrum, not a rough approximation. COBE, a satellite built to measure that spectrum above the blurring effects of Earth's atmosphere, delivered a remarkably clean result. The afterglow matched a near-perfect black body curve, which is exactly what you expect from a universe that was once hot, dense, and in thermal balance. Although that measurement was not visually striking, it was incredibly convincing to the mind. It is the kind of evidence that feels like a lock clicking shut. Once you have a thermal spectrum that's precise, many alternative explanations lose their footing. Additionally, COBE made it possible to ask more detailed questions. If the spectrum is that perfect, then the remaining details, like tiny anisotropies and polarization, become the next frontier for learning how structure began. COBE also found tiny temperature variations that later missions mapped in detail. Those minute mottlings in the cosmic background were a turning point because they were the first clear glimpse of the universe's original unevenness. The early universe was not entirely smooth, as COBE demonstrated. Faint patches of warmth and coolness were carried across the sky. That discovery mattered for a simple reason. Without early irregularities, gravity would have had nothing to build with. Once the variations were known to exist, scientists could treat them like fingerprints from a formative era. Their sizes and strengths revealed how matter and radiation interacted, and they offered clues about what ingredients the universe contained. It also changed what came next. In the same way that a blurry photo invites a sharper one, better missions were created to map the pattern with much finer detail. An entire precision science emerged from a tiny signal. WMAP refined the universe's age and composition using microwave maps. WMAP did not just take a prettier picture of the cosmic background. It measured the pattern so well that the ripples became a tool for taking the universe's inventory. Peaks and dips in the map trace how early matter moved, how pressure pushed, and how gravity pulled. By comparing the observed pattern with predictions, scientists could estimate how much ordinary matter exists, how much invisible matter is needed, and how dominant the mysterious, accelerating component must grow. Remove the stray B to quantifiable features in the sky. It also improved the estimate of the age of the universe. This was a shift from broad storytelling to precision bookkeeping. It provided a common point of reference as well. The work of various disciplines could be anchored to the same cosmic parameters, and numerical arguments became more precise and verifiable. A map of microwaves became a ruler for the whole universe's timeline. Planck pushed those measurements to even finer resolution. Planck took the cosmic background and measured it with extraordinary sensitivity across multiple frequencies. That matters because the sky contains distractions. Dust and energetic particles in our own galaxy can add foreground signals that must be separated from the true cosmic pattern. By observing in many bands, Planck could disentangle more of that clutter and reveal the background with greater clarity. Subtle physics is hidden in the small-scale features that it sharpened. Tiny differences in the pattern can tell you about how quickly the early universe expanded, how matter clumped, and how light scattered through the primordial plasma. Planck also strengthened the sense that cosmology is a high-precision field with numbers that can be compared to multiple decimals. That success came with a twist. Certain disagreements with other methods became more difficult to ignore as measurements became more accurate. Deeper mysteries can also be revealed by improved clarity. Big Bang nucleosynthesis predicts helium abundance seen in old gas clouds. The early universe produced a significant amount of helium during its first hot minutes, long before stars could produce it. A particular prediction is made by the theory. Given the density of ordinary matter, you should end up with a particular fraction of helium compared with hydrogen. Astronomers can test this by studying very old, very pristine regions of gas. These environments retain an early chemical record because they have not experienced much stellar processing. When the measured helium fraction matches the prediction, it is like finding a timestamp from the universe's infancy. that still reads correctly. The beauty here is that the physics is simple and strict. Nuclear reactions in a rapidly cooling cosmos leave limited room for improvisation. For this reason, helium abundance is more than just an interesting phenomenon. It is a consistency check that uses actual numbers from the sky to connect atomic nuclei to the biggest story conceivable. Deuterium measurements act like a cosmic baryon counter for normal matter. Deuterium is fragile. It is not produced in significant quantities by typical stellar processes and is readily destroyed within stars. That makes its cosmic abundance especially valuable because it mostly reflects what happened in the early universe rather than later recycling. The amount of deuterium that should survive is predicted by the theory of early element formation, and the answer is highly dependent on the number of baryons, protons, and neutrons per photon at that time. Measure deuterium in ancient, relatively unprocessed gas, and you can infer the amount of normal matter in the whole universe. It is like weighing the cosmos using a rare isotope as a scale. This is also why deuterium is treated with such care. Astronomers look for clean targets, and they cross-check results because a small observational bias could mislead a big conclusion. When the measurements agree, they pin down the baryon budget with remarkable confidence. Ancient ripples are used as a cosmic distance gauge in galaxy surveys. Not only are we gathering dots when mapping millions of galaxies, but we are also measuring the subtle preference for a specific separation scale that was established by early pressure waves. That scale acts as a standard ruler embedded in the distribution of matter. You can compare how big it appears at various distances if you know its actual size from early universe physics. That comparison reveals how the universe expanded across time. What makes this so powerful is that it does not rely on a single type of object. It uses statistics across vast volumes of space. It also links two eras. A characteristic that originated in the primordial plasma serves as a gauge for the galaxy-filled later universe. The surveys themselves are feats of patience and engineering. They record spectra, infer distances, and build three-dimensional maps. Cosmologists derive an expansion history, encoded in the cosmic web itself from those maps. Supernova observations revealed expansion is accelerating, not slowing. White dwarf explosions called Type Ia supernova can be used as distance indicators because their brightness follows a calibratable pattern. Teams discovered something shocking when they measured these explosions in very far-off galaxies. In a slowing universe, the supernova appeared dimmer than anticipated. The simplest interpretation was that the universe had been expanding more slowly in the past than it is now. This indicates that growth has been accelerating. This was not a subtle philosophical shift. It changed the expected fate of the cosmos and introduced a new dominant component to the energy budget. It also showed how the universe can surprise us using ordinary light. A star's death in a remote galaxy became evidence about the behavior of space itself. Caution was also required by the discovery. Astronomers had to rule out dust, evolution, and selection effects. The findings withstood that scrutiny and went on to become a pivotal moment in modern cosmology. Fitting multiple data sets simultaneously allows for the inference of cosmic parameters. Modern cosmology works like a courtroom with multiple witnesses. The cosmic background gives one kind of testimony, galaxy clustering gives another, supernova distances provide another, gravitational lensing adds yet another. Each data set has different sensitivities and different weaknesses, so combining them can break degeneracies that would confuse any single approach. When the fits converge, you obtain a set of parameters that describe the universe with surprising economy. Those numbers include the expansion rate, the matter fractions, and the amplitude of early fluctuations. Although the technique is effective, it also necessitates discipline. You must account for uncertainties, biases, and correlations. You need to make sure that improvements in one measurement don't mask mistakes in another. When done well, the result is a coherent cosmic model that can predict new observations. Cosmology feels both grand and meticulous because of this. It aims to describe everything, and it does so by carefully weighing many imperfect glimpses of the sky. Today, two exact methods of measuring expansion are at odds. One method measures the expansion rate by looking at the early universe and evolving a model forward. This uses the cosmic background and related physics as a starting point. Another approach uses a distance ladder to measure it locally. Distances to neighboring galaxies, calibrated supernovae, and pulsating stars can all be included in that ladder. Both approaches have become impressively precise, and that is the problem. They do not agree as well as they should. The gap is not enormous, but it is stubborn. It has survived years of improved data and careful reanalysis. This tension is significant because it implies that either the standard model of cosmology is lacking a component or hidden systematics still exist. It makes a number mysterious. It also makes the present era exciting. Precision is no longer only about tightening error bars. It is about deciding whether the universe is quietly telling us that our current story is incomplete. This discrepancy could be a sign of new physics that goes beyond conventional cosmology. If the expansion tension is not a measurement issue, then something in the cosmic recipe may need revision. A subtle new particle that changed conditions prior to the release of the cosmic background is one possibility, as is an early burst of extra energy that momentarily altered the expansion rate. Other theories include properties of neutrinos, dark sector interactions, or modifications to the large-scale behavior of gravity. Each proposal must do a hard thing. It must resolve the tension without ruining the many successes of the standard model. It maintains the integrity of speculation and sets a high standard. This is also how science advances. If a minor discrepancy can withstand rigorous testing, it may open the door to a more comprehensive understanding. For the time being, the disagreement functions as a recurring note in a chord that is otherwise harmonious. It may fade with better calibration, or it may grow into a new movement in physics. Either outcome teaches us something real. The universe likely had no preferred center. Expansion happens everywhere. The cosmic movie does not point to a specific location you could mark on a map, but it does bring everything closer together if you run it backward. Expansion is built into the geometry, so every galaxy can look out and see other galaxies receding in all directions. It is like raisins in rising dough. Every raisin sees the others drifting away as the dough swells, but no raisin is in the center of the loaf. This idea can feel slippery because our brains love a central stage. The universe refuses to provide one. The Big Bang is not a firework launched from a single location. In the sense that space was hotter and denser everywhere at once, it is an early state. That is why asking, "Where did it happen?" is frequently the incorrect question. The better question is, how did it change? Expansion does not mean galaxies fly through space like shrapnel. The idea of galaxies exploding into emptiness is alluring, but it is confusing. The crucial idea is that, even in cases where the galaxies are not pushing themselves apart, the space between far-off galaxies is expanding. Cosmologists claim that the universe expands rather than explodes because of this. It also helps explain a famous curiosity. Very distant galaxies can have a recession speed that seems faster than light, and relativity is still safe. Nothing is locally outracing a beam of light through space. Instead, the route between us and the galaxy is lengthening. You can picture it like an ant walking on a rubber band that is being pulled apart. The ant can obey every speed limit and still fail to reach the far end if the band stretches quickly enough. Expansion is motion of distance itself. On small scales, gravity can beat expansion and bind galaxies together. Unlike a wind that tries to tear everything apart, cosmic expansion is a large-scale phenomenon. Gravity and other forces maintain the structure of tightly bound matter while ignoring the universe's gradual expansion. That is why atoms do not expand. Your body does not expand, and solar systems do not drift apart because of the Big Bang. If the mutual gravity between galaxies is strong enough, even groups of galaxies can stay bound. This creates a universe with two simultaneous truths. On the grandest scales, distances grow and the cosmic web stretches. Islands of matter can orbit, collide, merge, and remain intact locally. It strikes a lovely balance. Gravity writes the local drama, while expansion sets the scene. Cosmology requires both geometry and dynamics, because understanding which effect predominates depends on scale, mass, and time. The Milky Way and Andromeda are moving closer despite cosmic expansion. If expansion were the only story, every large galaxy would drift away from every other one forever. Andromeda breaks that simple intuition. It is close enough and massive enough that local gravity dominates. The two galaxies are in the same neighborhood, along with smaller companions, and their mutual pull is drawing them together. Over time, their halos interact, and their paths curve inward rather than outward. This is not a contradiction of expansion. It is a reminder that the universe is not a single uniform motion. It is a tapestry of bound regions embedded in an expanding background. When the Milky Way and Andromeda finally collide, it will happen slowly, on human timescales, changing both galaxies through long arcs of stars thrown into new orbits, star formation, and tides. It is a future written by gravity, happening inside a universe that still expands around it. The early universe produced no heavy elements beyond lithium in quantity. The periodic table was nearly empty at first. The first minutes could make hydrogen and helium efficiently, and it could leave behind only a small trace of lithium. Then the universe cooled too quickly for heavier nuclei to be built in that global way. There were repercussions to this early simplicity. Without abundant heavier elements, there were few efficient ways for gas to radiate heat away, and heat matters because cooling helps clouds collapse. Under these limitations, the first structures had to form with a small set of chemical tools. It also implies that every heavy element you have ever encountered, from silicon in sand to calcium in bone, is a later creation of the universe. The early universe set the initial conditions, but it did not supply the ingredients for rocks, oceans, or biology. Those came later, after generations of stars learned how to manufacture complexity and return it to space. Later, stars used nuclear fusion to create carbon, oxygen, and iron. The universe gained long-lived factories that could maintain hot, dense nuclei for millions to billions of years after stars formed. Inside stellar cores, hydrogen fusion provides the first major energy source. As massive stars develop, helium is converted to carbon, which is then converted to oxygen and neon, and finally to elements like silicon and magnesium. Iron represents a unique turning point. Iron fusion places a limit on what regular fusion can achieve in a star's core, because it releases energy differently than lighter fusion. That limit shapes stellar endings. It also shapes life, because carbon chemistry underpins biology, oxygen drives metabolism, and iron becomes a common component of planetary interiors and many living systems. When you consider the Big Bang, it's important to keep in mind that stars provided the rich middle, transforming a mostly hydrogen universe into one with a variety of materials and endless possibilities. Many elements heavier than iron were produced by neutron star and supernova mergers. To build elements heavier than iron in large quantities, the universe needs environments more extreme than a steady stellar core. Two of the leading sites are dramatic. One is when a massive star dies in a supernova, where extreme conditions and shock waves can cause fast nuclear reactions. Another is when neutron stars collide, sending matter that has been compressed to almost nuclear density, flying outward and flooded with neutrons. In such places, nuclei can capture neutrons quickly and then transform into heavier elements as they settle into stability. Many rare heavy elements, including some found in jewelry and electronics, are thought to form in this way. Astronomers look for these fingerprints in the light from explosive events and in the chemical patterns locked into ancient stars. Each detection is like finding a shipping label from a cosmic foundry. The heavy elements in the world around you are not generic. They are mementos of violence woven into the fabric. The first black holes may have grown rapidly from early massive stars. Massive stars may have lived quickly in the early universe due to favorable conditions. Collapsing into black holes is how many end. If those first black holes formed early enough, and if they found abundance surrounding gas, they could grow quickly by feeding. The reason this resonates through the ages is we observe quasars very far away, which means we see them very early in cosmic time, and some host black holes that are astonishingly massive. That presents a conundrum. How did they grow so big so soon? Rapid accretion, in which gas spirals in and releases massive amounts of energy, is one route. Frequent mergers of smaller black holes in dense early environments are another possibility. These ideas turn black holes into characters in an origin story. They are not only endpoints of stars. They may be architects of early galaxies, influencing star formation by heating and stirring gas with powerful radiation and jets. The cosmic neighborhood that the first black holes inhabited may have been shaped by them. Some models allow primordial black holes formed before the first stars. There is another, more speculative route to black holes, and it begins even earlier than starlight. In theory, gravity could directly crush some of the slightly denser than average regions in the early universe into black holes without the need for stars as a middle step. The masses could vary widely depending on when they formed. Some would evaporate quickly through quantum effects, while others could survive to the present. This theory is intriguing because it relates a current mystery to early universe physics. It implies that black holes may contain information from times and environments that are impossible for us to observe with regular light. Additionally, it is a concept that encourages experimentation. Primordial black holes would leave signatures through gravitational lensing, through their influence on structure, or through subtle effects on cosmic backgrounds. The models serve as a reminder that there is still space for surprises in cosmology, particularly with regard to what formed first. If primordial black holes exist, they could contribute to dark matter. Dark matter is known by its gravity, and black holes are gravity in a concentrated form. So it is natural to ask if some fraction of the missing mass could be black holes made in the early universe. The problem is that the concept needs to endure numerous limitations. We would anticipate more background star lensing events, effects on the cosmic background, or disruptions in stellar systems, if there were too many primordial black holes with particular masses. Many possibilities have been ruled out by observations, but not all of them. There are still areas of parameter space where primordial black holes might be relevant. Even a partial contribution would be exciting because it would tie dark matter to an object we already understand in general relativity. It would also make dark matter less like an invisible particle and more like a population of hidden compact objects. In any case, the search improves our understanding of the composition of the universe. Cosmic background anisotropies reveal the universe is very close to flat. The cosmic background's mottled pattern is more than just a lovely map. It's a test in geometry. The way light and distances behave in curved space affects how big early patterns appear in the sky. Scientists find that the background's characteristic sizes match what would be expected if space is generally very nearly flat. That does not mean the universe is simple. It means the large-scale geometry does not noticeably curve like a sphere or saddle within our measurement precision. This is astonishing because slight curvature could have grown important over cosmic time. Rather, the universe appears to be perfectly balanced. Because a quick early stretching would inevitably push space toward flatness, similar to removing wrinkles from fabric, this result also relates to early expansion theories. A subtle pattern in the sky makes a statement about how reality is shaped. Flat does not imply that the universe is shallow or small. Rather, it refers to geometry. When people hear flat, they picture a pancake universe with edges you could fall off. In cosmology, the word is about geometry. It describes how parallel lines behave, how triangles add up, and how light paths compare with the rules you learned in school. A flat universe follows the familiar geometry of Euclid on large scales. Light does not curve due to global geometry alone, and triangles add up to roughly 180 degrees. That has nothing to do with whether the universe has an end, or whether it is wide in some direction and narrow in another. Flat is also not the same as empty. A flat universe can still be packed with matter, radiation, and mysterious components, and all of them can influence how expansion evolves. It serves as a reminder that common language in science can be misleading. Sometimes, the most important meaning is the one you cannot picture easily, but you can measure. Flat space can still be infinite, depending on global topology. Geometry tells you about local rules, but topology tells you about the overall layout. A flat surface can be infinite, like an endless plane, but it can also be finite if space connects back on itself in the right way. A classic analogy is a video game world, where walking far enough in one direction brings you back to where you started. While it loops globally, it can feel flat locally. Some cosmological models allow a universe like that in 3 dimensions, where space is flat in its geometry, but still wraps around. If that were true, they could be repeating patterns in the sky, like the same distant region appearing in multiple directions at different times. Finding such patterns is challenging, and no conclusive results have been discovered, but the concept is exciting. It shows how the universe could be both bounded and edgeless, with flatness and finiteness coexisting. We have not measured whether the universe wraps around itself. There may be a cosmic shortcut in space where you can eventually return home after traveling far enough in one direction. If that were the case, the sky might contain subtle clues, like matching circles or repeating arrangements in the background glow created, because light took different routes through a looping space. The challenge is that the universe is vast, and we only observe a finite region. If the wraparound scale is larger than what we can see, then the evidence would be out of reach. The intricacy of light scattering in the early universe and noise foreground interference could obscure the signal, even on a smaller scale. So this becomes a fascinating kind of absence. We can test certain possibilities, rule some out, and leave others open. It is a reminder that cosmology does not only ask what happened, it also asks, what kind of space are we living in? The answer might be stranger than distance alone suggests. The cosmic neutrino background should exist, though it is extremely hard to detect. Neutrinos resemble ghosts. Every second, trillions flow through you, but you feel nothing. Neutrinos were created in enormous quantities in the early universe, and as space expanded, they cooled into a relic background that was even more elusive than the cosmic microwave background. Interaction makes a difference. We can use antennas and detectors to capture photons because they scatter readily. Neutrinos barely interact at all. So a true primordial neutrino background is extraordinarily difficult to observe directly. Yet, its existence is not just a wish, it is a robust prediction of early universe physics. Even if we come to bottle, or better, directly detect these relic neutrinos, their effects can still be inferred. They influence how quickly the universe expanded during key eras, and they slightly alter the growth of structure. In that way, an unseen ocean can still leave tidal marks. Finding it would be like listening to the earliest chorus of the universe on a deeper level. Under extreme circumstances, particle physics describes the earliest moments. The universe was not initially made up of a collection of galaxies. It was a lab where particles, fields, and energy were continuously changing into one another. Because the temperatures were so high that ordinary matter could not exist in familiar forms, the rules of particle physics are the most important. The ingredients list of reality may have been different, with particles appearing and disappearing as conditions changed. This is why cosmology and particle physics are intertwined. When cosmologists ask what happened very early, they often end up asking what particles existed, how they interacted, and what symmetries held. When particle physicists test high-energy theories, they often ask what those theories would have done to the infant universe. It is a cross-scale collaboration. The biggest thing we can examine serves as proof of the tiniest laws, and the tiniest laws tell a tale about the entire sky. The Big Bang model does not yet explain why constants have their values. The model describes how the universe evolves given certain rules, but it does not fully explain why the rules are set the way they are. Why does gravity have its particular strength? Why do particle masses take the values they do? Why does the vacuum behave as it does? These numbers shape everything. Small changes could prevent stable atoms, alter stellar lifetimes, or erase the chemistry that makes complex structures possible. Scientists explore many ideas here. Some look for more profound unifying theories that would render the constants unavoidable. Others wonder if our observed values might have been chosen from a larger range of options. This question is fascinating because it sits at the edge of what science can currently test. It is not a weakness of cosmology. It is a frontier. The Big Bang story tells us how the universe grew up. Why this universe had this specific personality in the first place is the question of constants. Furthermore, it doesn't explain why there is more matter than antimatter. Matter and antimatter are frequently treated as mirror partners by the laws of physics. In the early universe, they were created together in abundance, and they could annihilate back into radiation. If the balance had been perfect, you would not have stars, planets, or air. Most of it would be light. Yet the universe clearly ended up with a leftover supply of matter. That leftover is everything solid you have ever touched. Whether it occurred or not is not the mystery. The mystery is how. The process must have involved physical effects that marginally favor matter over antimatter, and must have taken place in an environment that permitted minute asymmetries to become permanent. Because it links existence itself to minute microscopic behavior, this is one of the most exciting open problems. It also shows how cosmic history depends on tiny differences. A small imbalance early on becomes a universe with structure later. Solving this would connect the first moments to the fact that anything remains at all. Baryogenesis is the name for processes that could create that imbalance. This is the umbrella term for the universe's method, whatever it was, for tipping the scales toward matter. Strict requirements must be met for any mechanism to be successful. It must permit a change in the matter number. It must treat matter and antimatter differently. Additionally, the universe cannot easily undo it because it must happen out of equilibrium. Those conditions are demanding, and they make baryogenesis a powerful filter for theories beyond the standard model of particle physics. Different ideas place the action at different times. Some associate it with very early phase changes, others with neutrino physics, and still others with physics at energies much higher than those achievable in accelerators. What makes this captivating is the detective nature of the search. The universe as a whole is the crime scene, and the evidence includes the existence of galaxies, as well as minute symmetry violations measured in labs. Every improved measurement narrows the suspect list. The goal is not a clever story. It is a mechanism that fits nature's rules and the universe we observe. Early phase transitions may have changed the universe's forces. As the universe cooled, it likely passed through threshold moments where the behavior of fields changed and new distinctions emerged. In everyday life, water freezing is a phase transition. Transitions in the early universe may have involved the forces themselves, altering particle interactions and the appearance of characteristics like mass. These events could have released latent energy, formed exotic defects, or produced new particle populations. They might also have influenced baryogenesis if the conditions were right for matter to gain an advantage. The concept is dramatic because it implies that as the universe cooled, its basic laws were being rearranged. This is also why cosmologists care about symmetry. At high energy, symmetry may exist, but as the universe expands, it may break, leaving behind new physics at lower energies. If we could map these transitions more clearly, we would be reading a timeline of the universe, learning what kind of universe it would become. The electroweak era shaped how particles gained mass through symmetry breaking. Very early on, the universe was so hot that forces we now treat as separate behaved as one combined electroweak force. A field that fills space settled into a new state as expansion cooled everything. And this change altered the way some particles traveled through it. Some particles began to experience resistance that shows up to us as mass. Photons stayed massless, which is why light can travel freely across the cosmos. Other particles gained mass, which helped shape what could exist later, from stable atoms to long-lived stars. This is one of the strangest ideas in physics, because it means mass is not only a property of an object, it is also a relationship between an object and the state of space itself. In addition to creating matter, the early universe established the laws that matter must abide by. Quark-gluon plasma once filled the cosmos before protons could form. Before there were protons, the universe was too hot for quarks to stay confined inside them. The typical particle boundaries were not yet set in stone, as quarks and gluons moved in a dense, energetic mixture. Then cooling pushed the universe through a transformation. The universe acquired the well-known building blocks of later chemistry, when quarks were bound into hadrons, which included protons and neutrons. This transition is sometimes compared to steam condensing into liquid, not because it is the same process, but because the whole character of the material changed as temperature fell. The idea that every proton in your body originates from a period when protons were not possible is absurd. The universe had to pass a thermal threshold before it could even form the particles that would later form atoms. That long-ago transition from free quarks to confined matter is essential to our solid world. Particle colliders recreate tiny echoes of early universe conditions. Although we are unable to rewind the universe on Earth, we can temporarily replicate some of its early components. In heavy ion collisions, nuclei are smashed together at enormous energies, and the impact can briefly produce a state of matter closer to the early universe than to everyday solids and gases. Detectors then watch what sprays out, and those particle patterns act like clues to what the hot phase was like. Researchers look for signs of collective flow, energy loss, and other behaviors that suggest matter is acting as a strongly interacting fluid rather than a simple gas of particles. It is remarkable that a machine built on a planet can probe conditions that once filled the entire universe. Colliders turn cosmology into an experimental science in miniature. They cannot reproduce the whole early universe, but they can test pieces of its physics, and pieces can still change the story. The cosmic background is not light from the first stars. Given that both involve extremely old light, this frequent confusion makes sense. The cosmic background originates from an era prior to the existence of stars. It was released when the universe was still a hot, nearly uniform sea of matter and radiation, long before galaxies had assembled. Starlight, by contrast, is produced inside stars and carries fingerprints of stellar atmospheres like sharp spectral lines and distinctive colors. The cosmic background is different. It is an all-sky glow with a near-perfect thermal spectrum, and it does not point back to individual sources. It points back to a time when the universe itself was the source. Keeping this distinction clear matters because it changes what the signal can tell us. We learn about chemical history and astrophysics from starlight. The background teaches us about the early conditions that set the stage for everything that came later. It is older. It comes from when the universe first cleared. There was a moment when the universe stopped acting like a fog and started acting like transparent space. Light could not travel very far before then without getting dispersed. Thus, the universe was both bright and visually confined. Photons began to flow freely when circumstances changed, and they have been doing so ever since. What we observe today is sometimes called the surface of last scattering, not because it is a physical wall, but because it marks the last time those photons were repeatedly bounced around. It is also a strange kind of time machine. No matter where you look, you are seeing a shell of that same era at different points in space. Even nearby directions in the sky correspond to regions that were far apart back then. This explains why the shell's subtle pattern is so instructive. Once the universe cleared, a sky full of evidence was left behind. The visible light afterglow has been extended into microwaves. As the universe expands, it stretches wavelengths in transit, like a tune lowered as the instrument grows. Hotter radiation peaks at shorter wavelengths, and the cosmic background started out much hotter than it is today. These wavelengths were extended over billions of years by expansion until they entered the microwave band. This stretching also cools the radiation in a predictable way, because longer wavelength light carries less energy per photon. Because of this, the current background temperature is only a few degrees above zero. It is not because the universe cooled like a room losing heat into outside space. It cooled as a result of space's expansion, which stretched light and diluted energy. The result is a signal that is both ancient and current, arriving right now as microwaves from every direction. With the right instruments, we can measure that ancient heat long after it faded from visible brightness. As space expands, it also stretches wavelengths, creating cosmic redshift. Redshift is the universe's built-in stamp on traveling light. When a galaxy emits light, that light begins its journey with a certain wavelength. The wave is stretched along with the expanding scale of space as it moves. By the time it arrives, its wavelength is longer, and its color has shifted toward the red end of the spectrum. This is not only an effect of motion through space, it is an effect of the changing geometry of space during the journey. That is why redshift is so central to cosmology. It links what we measure in a spectrum to the history of expansion between then and now. It also gives every photon a story. The light left a different universe than the one it arrived in, and the stretching of its wavelength is the trace of that change. In a way, every far-off beam bears the name of the universe. Redshift is how we tell distant galaxies are seen in the past. Astronomers search for identifiable characteristics, such as patterns from hydrogen or other common elements. When they spread a galaxy's light into a spectrum, those features appear shifted compared with laboratory measurements. The galaxy's redshift is determined by the amount of shift. And once a cosmological model is adopted, redshift can be translated into the length of time that light has been traveling. That gives a look-back time. It is one of the few ways we can place distant objects on a timeline without knowing their full histories. With redshift, a deep survey becomes a kind of layered museum. Nearby galaxies represent later chapters, while high redshift galaxies reveal earlier stages of growth and change. This is also why the same telescope can study both structure and history at once. By measuring redshifts, we do not only map where galaxies are, we map when we are seeing them. The sky becomes an archive, and distance becomes time. The first molecules formed before the first stars, including simple hydrogen molecules, chemistry, managed to start even in a universe with very few heavy elements. As the cosmos cooled and neutral atoms became common, small numbers of molecules could form, especially molecular hydrogen. The process was inefficient, but it did not need to be fast to matter. A tiny fraction of molecules can have an outsized effect because molecules can radiate energy through rotational and vibrational transitions. There were also more exotic early molecules, like helium hydride, which may have been among the first molecular bonds in the cosmos. The fact that these early molecular processes took place in the dark before planets and starlight makes them fascinating. They show that complexity does not begin with biology. It begins with the universe becoming cool and stable enough for atoms to stick, then for molecules to form, and then for new pathways to open. Chemistry did not wait for stars to turn on. It started assembling in the shadows. Cooling by those molecules helped the earliest stars collapse and ignite. Gravity can pull gas inward, but without a way to lose heat, a collapsing cloud builds pressure and can stall. Early molecules, especially molecular hydrogen, gave primordial gas a way to radiate energy away. That cooling allowed clouds to contract further, reach higher densities, and eventually trigger star formation. The first star-forming regions were likely small halos of dark matter filled with simple gas, and molecular cooling helped that gas settle into dense cores. This does not mean molecules did all the work. Gravity provided the pull, and the expanding universe set the timing. The energy escape hatch was made possible by molecules. The result was the first ignition of starlight, which then began transforming the universe in new ways. This is one of the most satisfying chains in cosmic history. Expansion cools the universe. Cooling makes molecules possible. Collapse is made possible by molecules. Collapse allows stars. And stars begin the long story of heavy elements, planets, and the conditions that make complex worlds possible. Reionization is when early starlight stripped electrons from atoms again. After the universe first became neutral, it did not stay that way forever. Gas continued to accumulate due to gravity, and in certain areas of the cosmic web, the first luminous sources turned on. Their energetic ultraviolet light began tearing electrons away from hydrogen once more. This did not occur all at once. It spread like overlapping bubbles, growing around young galaxies and star-forming regions. Neutral gas persisted longer in some locations and disappeared sooner in others. This patchiness is important because it modifies the ease with which gas can cool and collapse, as well as how later light moves through space. Astronomers chase this era using clever signals, including the way neutral hydrogen would glow or absorb at a radio wavelength called 21 centimeters. When we map reionization in detail, we will be watching the universe wake up again, not with a single sunrise, but with many. Quasars helped reionize the universe by pouring out intense radiation. Quasars are powered by supermassive black holes, feeding on infilling gas. As material spirals inward, it heats to extreme temperatures and shines across the spectrum, including strong ultraviolet and X-ray light. Because their photons have enough power to remove electrons from distant atoms, quasars are therefore natural ionizers. Large ionized regions in the surrounding gas could have been carved in the early universe by even a few bright quasars. They also give us a way to test the state of the cosmos. When we look at very distant quasars, we sometimes see a deep absorption feature from intervening hydrogen. It indicates that neutral gas was still prevalent along the line of sight and is known as the Gunn-Peterson trough. So quasars play two roles at once. They may have helped change the universe, and they also act as backlights that reveal how much of that change had already happened. Cosmic background polarization carries information about early scattering events. The cosmic background is not only a temperature map, it also has a faint pattern in the orientation of its electric field created when light scattered off electrons under slightly uneven conditions. That polarization is precious because it separates different kinds of history. One pattern, called E-modes, is produced naturally by density variations in the early plasma, and it has been measured with impressive clarity. Another pattern, called B-modes, is harder to make and can be generated by gravitational lensing or by primordial gravitational waves if they exist. There is also a feature tied to reionization. When the first galaxies reionized the universe, newly freed electrons scattered background light again, and that adds a large-scale polarization signature. So polarization is like a second script layered on top of temperature. It helps break degeneracies, test inflation ideas, and reveal how the universe changed long after the first clear light was released. Gravitational lensing distorts the background, revealing hidden mass along the way. As ancient light travels to us, it passes through a universe filled with matter, both visible and invisible. Photon paths are deflected by the bending of space-time caused by gravity. The result is subtle warping of the background pattern. Hot and cold spots get slightly shifted, and sharp features become gently smeared. This is a measurement, not an annoyance. Scientists can reconstruct a map of the total mass that underwent the bending, integrated over enormous distances, by examining the statistical distortions. What makes this so exciting is that lensing responds to gravity, not to brightness. It doesn't care if the mass is entirely dark or shiny and dusty. It is only concerned with the presence of the mass. So the cosmic background becomes a backlit screen, and the entire universe between us and that screen becomes the lens. With enough precision, lensing even lets us test how structure grew over time and whether gravity behaves exactly as expected on the largest scales. That lensing map is one of our best traces of dark matter. An X-ray of the cosmic web is comparable to a lensing reconstruction. It highlights where mass is concentrated, even when ordinary matter is faint or missing. When researchers compare lensing maps with galaxy surveys, they can see how luminous matter sits inside larger dark matter structures, and they can quantify the bias between light and mass. Lensing also helps constrain key numbers that describe clustering in the universe, including how strong the typical density variations are on certain scales. It can even put pressure on the masses of neutrinos, because heavier neutrinos subtly suppress small-scale structure and leave fingerprints in the lensing signal. Another strength is its cleanliness. Lensing avoids making assumptions about how bright objects should be and does not rely on the intricate astrophysics of star formation. It simply follows gravity. That is why it has become central to modern cosmology. When you want to map the invisible, you look for how it bends, what is visible. The universe's expansion history affects how structures grow over time. Gravity is always trying to pull matter together, but expansion acts like a moving floor that can make collapse harder. Matter has less time to clump before distances grow farther if the universe expands more quickly to a given era. If expansion is slower, gravity has more opportunity to amplify small differences into large structures. Cosmologists describe this with a growth factor, which tracks how density variations strengthen as the universe ages. Growth can be measured in a number of ways, such as how galaxies cluster, how their motions distort redshift space, and how lensing signals change with distance. This is why expansion is not only about where galaxies are, it is also about what galaxies can become. Cosmic webs would develop differently in two universes, with identical components but distinct expansion histories. When we combine measurements of expansion with measurements of growth, we get a powerful consistency test. Disagreement between the two stories may indicate new physics or a missing component in the cosmic recipe. Dark energy suppresses growth by pulling space apart faster. When dark energy dominates, expansion accelerates, and that changes the future of structure. Matter can still collapse in already bound regions, but new growth on very large scales slows down because the universe is stretching too quickly for gravity to gather fresh material efficiently. It can be compared to the cosmic web's inability to tighten its threads. This repression goes beyond philosophy. It leaves measurable traces. It changes how clustering evolves with time, and it can create a subtle effect on the cosmic background called the integrated Sachs-Wolf effect, where photons gain or lose energy as gravitational potentials evolve. Dark energy also affects how we interpret surveys, because the same set of early seeds can lead to different present-day structures depending on how acceleration turned on. Thus, dark energy is more than just an expansionary force. It is a shaper of what never forms. It influences the amount of large-scale structure the universe is allowed to build. Some theories replace dark energy with modified gravity on cosmic scales. Instead of adding a new energy component, some ideas tweak how gravity works over very large distances. In these models, acceleration emerges because gravity behaves differently than general relativity predicts when space is vast and densities are low. The challenge is that any modification must hide in places where Einstein's theory has been tested extremely well, like the solar system, while still changing cosmic behavior. Many proposals use screening mechanisms that make deviations small in dense environments and larger in the emptier cosmic background. By contrasting various methods of weighing the universe, these theories can be put to the test. While lensing reacts to space-time curvature, galaxy motions respond to the gravitational force. In modified gravity, these two can diverge. Researchers look for mismatches between dynamical mass and lensing mass, and for changes in the growth rate of structure. This is an exciting possibility because it would imply that there is no mysterious energy driving the universe. It would mean our map of gravity itself needs a cosmic scale correction. Cosmology is frequently tested and depends on the assumption of large-scale uniformity. According to the cosmological principle, the universe is essentially the same everywhere on the largest scales, with no unique location or direction. It is not a leap of faith to make this assumption. It has been examined. The cosmic background is extraordinarily uniform after removing local motion effects. Galaxy surveys show that while matter is clumpy on smaller scales, the distribution approaches homogeneity when you average over truly huge volumes. Researchers also test isotropy by comparing expansion measurements in different directions and by checking whether the statistical properties of cosmic maps depend on where you look. These tests are important because the principle governs how we calculate distance from redshift and deduce the general parameters of the universe. Numerous conclusions would need to be re-examined if the universe was significantly anisotropic or inhomogeneous on the largest scales. So cosmology treats uniformity as a working hypothesis with receipts. The universe seems to cooperate, but scientists keep checking because the stakes are high. It is possible to measure even minute deviations from uniformity throughout the sky. Once you have accurate maps, you can ask whether the universe is statistically uniform or only very nearly so. Scientists search for hemispherical asymmetries, preferred directions, and subtle deviations from a purely random Gaussian pattern in the early fluctuations. They also look for traces of cosmic defects or hints that inflation left non-standard signatures. Many of these searches run into a fundamental limit called cosmic variance, which is the simple fact that we have only one universe to observe, so some patterns can look unusual by chance. Even so, the measurements are sharp enough to place strong bounds on many exotic possibilities. One of the most intriguing features of contemporary cosmology is this. It can use subtle patterns dispersed throughout the entire sky to test theories regarding the first instance. The universe becomes a precision instrument, and we become its careful readers. When a tiny departure is claimed, the community demands overwhelming evidence, because small anomalies can teach us everything or nothing at all. Regarding what transpired prior to the beginning of time, the Big Bang model says nothing. People are asking a very human question when they ask what came before, and physics carefully pauses before responding. The Big Bang model describes how the universe evolves from an early hot, dense state. It does not automatically provide a chapter titled "Earlier Than Time," because in many versions of the story, time itself is part of what emerges. Since the meaning of before depends on time that has already passed, you cannot point to it in that situation. That does not mean curiosity is unwelcome. This indicates that the question pushes us closer to the point at which our existing theories become unreliable. To go further, scientists look for a deeper framework that can describe the earliest instance without breaking down. Until then, the model stays honest. It tells us what it can, and it refuses to invent what it cannot test. Some proposals replace a beginning with a bounce from contraction. One alternative picture imagined a universe that was once shrinking, then reached a turning point, then began expanding. According to this perspective, the Big Bang is not the absolute beginning. It is the moment the direction changed. The appeal is that it might avoid an initial singularity, and it might offer a natural explanation for why the universe looks so smooth on large scales. The hard part is the bounce itself. At extremely high densities, ordinary physics may not be enough, so these models often rely on quantum gravity effects that are still being developed. They also face a memory problem. If a prior universe existed, what information could survive the crushing contraction, and what would be erased? Researchers look for telltale patterns that a bounce might imprint on primordial fluctuations, because a viable idea must offer predictions, not only a different story. It is a daring possibility. It turns the origin into a transition, and it asks the cosmos to be cyclic rather than one time. Other proposals suggest inflation continues elsewhere, creating many bubble universes. In some versions of inflation, the rapid expansion does not end everywhere at once. It ends in pockets, like raindrops forming in a cooling cloud, while the larger inflating space keeps expanding. Each pocket can become a universe region with its own hot start, while other regions remain in the inflating state. These pockets are often described as bubble universes, and the wider inflating background is sometimes called eternal inflation. Because it reframes our universe as one area among many, rather than the entire show, the concept is dramatic. It also provides a possible explanation for why the universe appears to be set up to support complex structures. Some bubbles may be inherently more hospitable than others, if there are numerous bubbles with various effective qualities. The challenge is evidence. If other bubbles exist, they may be causally disconnected from us. Scientists therefore look for indirect signatures, such as subtle scars that a past bubble collision might leave in cosmic background patterns. It is speculative, but it is not casual. It lives or dies by whether it can be tested. Because multiverse theories can be challenging to test, they are controversial. Science thrives on predictions you can check, so the multiverse raises a sharp question. If other universes exist beyond our observable horizon, how could we ever gather evidence? The controversy resides there. Some researchers argue that if a theory, which is otherwise well supported, implies a multiverse, then the multiverse is part of the package, even if direct tests are limited. Some contend that when a theory can explain nearly anything after the fact, it loses its scientific validity. The debate is not only philosophical, it influences how people choose models, what counts as an explanation, and what kinds of evidence are considered acceptable. Additionally, there are middle paths. Some multiverse scenarios might leave traces, such as collision signatures or statistical predictions about certain parameters. Those would bring the idea back into the realm of measurement. For the time being, it is still a frontier where humility and physics inference collide. It invites wonder, and it demands rigor. The earliest fraction of a second is beyond current direct observation. We can see the universe back to when it became transparent to light, and we can infer earlier conditions through relics like element abundances and background patterns. Still, there is a curtain we cannot lift with present tools. We do not yet have a fully verified theory of quantum gravity to lead us there, because the early instants were so energetic that they pushed the boundaries of our best-tested theories. Because of this, cosmologists view the first tiny slice of time as a place of educated speculation rather than established truth. Yet, it is not a blank. Particle physics provides constraints, and observations restrict what could have happened, because later evidence must be consistent. Researchers use this approach like archaeology. Although you are unable to witness the earliest moment, you can examine what it left behind and eliminate possibilities that would have resulted in a universe that differs from our own. The boundary is real, but it is not the end of knowledge. It is the start of the hardest questions. Yet the later fingerprints are clear in light, elements, and structure. The universe left a trail that gets easier to read as it expands, even if the initial moments are hidden. Ancient light carries patterns from early conditions, preserved across the entire sky. The mix of the lightest elements records nuclear reactions that happened when the universe was young enough for the whole cosmos to act like a reactor. The distribution of galaxies reveals how tiny early differences grew under gravity into filaments, clusters, and voids. These are not separate stories. They are cross-checks that connect different eras. The later fingerprints must have a different appearance if the initial conditions are altered. That is why modern cosmology feels so compelling. It is not based on a single clue. It is built from independent records that must agree. When they do, the universe becomes a coherent narrative, rather than a collection of mysteries. The universe has been leaving evidence ever since. Even though we are unable to directly witness the beginning, the universe is currently expanding and will continue to change for eons to come. Expansion is not only a historical event, it is the universe in its present tense. The universe's contents influence the rate at which the distances between distant galaxy groups continue to grow. Over immense time, expansion changes what kinds of interactions are common. It affects how often galaxies collide, how easily matter can gather into new structures, and how the cosmic web evolves. What propels the expansion will determine the future. If acceleration continues, the largest scale structure will gradually freeze out, with fewer new connections forming between distant regions. Locally, though, gravity will keep crafting its own stories. Bound systems can continue to orbit, merge, and form stars until their fuel runs low. This is one of the strangest truths to sit with. The Big Bang is not only about a beginning, it tells the story of a universe that is still developing, expanding, aging, and transforming its initial conditions into a protracted, gradual future. Far future galaxies may disappear from view as horizons grow. If cosmic acceleration persists, there is a quiet consequence that feels almost poetic. Light from very distant galaxies may never reach us, not because it stops being emitted, but because the space it must cross grows too quickly. Over enough time, more galaxies slip beyond a cosmic event horizon, and their signals fade away from our reachable universe. Observers in the far future could look up and see a much emptier sky than we see now. They might not detect the cosmic background easily either, because it will be stretched to much longer wavelengths and become harder to measure against local noise. That future emptiness would not mean those galaxies cease to exist. It would imply that although the universe continued to expand, the observable universe actually shrank. This idea changes how you think about astronomy. Nowadays, evidence for cosmic history can still be seen over great distances. The universe is generous now in a way it may not be forever. One day, accelerated expansion may make the night sky appear more empty. Imagine a civilization that arises trillions of years from now in a bound galaxy group. The larger universe may appear nearly invisible to them. Only local stars and remnants would remain after the closest external galaxies vanished beyond the horizon. Inferring expansion would be more difficult in the absence of a rich field of far-off galaxies. It would be more difficult to reconstruct a hot early phase in the absence of an easily observable cosmic background. Their cosmic evidence would be weaker, even if they were still very good at physics. This is more than just conjecture about the distant future. It is a reminder about timing. Because we can still map large-scale structure across vast volumes and see deep into cosmic history, our current epoch is unique from an observational standpoint. The accelerating universe may eventually hide that grandeur from view. In that way, cosmology is partly a science of opportunity. The universe offers clues for a time, and then geometry slowly locks some of them away. The Big Bang is not only a beginning story, it is a measurement story. At its heart, this topic is about how we know what we claim to know. Cosmology takes faint signals and turns them into a timeline, a composition, and a geometry. It accomplishes this by viewing the cosmos as a physical system with testable laws. Early conditions are recorded by background light. Element abundances become a check on early nuclear reactions. Galaxy clustering becomes a map of growth under gravity. Since there is uncertainty in every measurement and potential bias in every method, the true strength lies in the agreement between various approaches. The Big Bang model has persisted because of this. It makes predictions that can be checked, and it survives those checks better than its rivals. It also keeps evolving as data improves. When new measurements disagree, the model is not threatened by questions. It is sharpened by them. Although the narrative is ambitious, it is based on attentive listening to the sky. As we reach the end of this journey, take a moment to notice just how far we've traveled. From a universe that began hot and dense, to one threaded with galaxies, light, and time itself. We traveled through times when the first stars ignited, when darkness persisted, when atoms first formed, and when space discovered how to continue expanding. We followed the development of structure from simple beginnings, the formation of patterns by gravity, and the continued whispering of ancient signals across the heavens. It all serves as a reminder that the universe is not hurried. It unfolds slowly, patiently, across unimaginable spans of time. And in that vastness, there is room to let go, room to soften the day, to release the weight of thinking, and to rest inside something much larger than any single moment. If you find yourself still awake and curious, another video is waiting for you on the screen, ready to carry you gently onward. And if these quiet explorations bring you comfort, you might consider liking the video, subscribing, or leaving a thought below. It helps this little corner of calm reach others who may need it. For now, there's nowhere you need to go. Allow the pictures to fade. Let the ideas settle. Let your breathing slow, and your mind wander like far-off galaxies that are steadily expanding and getting quieter. For today, you've accomplished enough. Sleep well, and good night.